Okay folks, welcome to lecture 11, and in this lecture we're going to take a look at logarithms, or logs as they're more commonly known. They're very important in science, maths for science. First of all though, we just take a look when sums go bad. And the Ariane 5 rocket explosion is a particular example. This is the aftermath. So it didn't quite make it into space. And the rocket was carrying 4 satellites. So in total it was worth nearly 400 million. And the error that caused it was an integer overflow error. So essentially they used old software. They didn't update the software. And this new rocket was generating much higher figures than the software could handle. And as a result, it simply went into self-destruct. So the reason they'd used the software before in the older types of rockets, and it worked fine, but they didn't really realize that their new, faster, bigger, faster rocket would generate bigger, faster numbers. And as a result, the computer system couldn't handle it. Very good explanation of it here. Really goes into the integer error, integer overflow error, etc. So it gives you a good idea of what happened. So now we're just going to take a look at logs proper, but I'm just going to try and introduce where they live in the world of maths really. So they're essentially an inverse of a power function, but we'll take a look at what I mean. So here guys, if we have this statement here, 10 plus 5 gives us 15, we can undo the work done by this plus 10 by applying the inverse. We can say 15 minus 10 brings us back to where we started. Similarly, if we had 5 multiplied by 10 gives us 50, we can undo this work. We can kill that multiplied by 10, and how we do that is we divide by 10. So 50 divided by 10 brings me back to where I started. I've undone. So this function and this function applied sequentially undo each other. Similarly, if we had 10 squared is 100. Now, it's important here, guys, there's 2 bits to this statement. There's the base and there's the power. So if we want to kill the power, we can use a square root. So the inverse of squared, as we've seen, is square root. And similarly, guys, we could have used the power version, and that would have got us there as well, because these are the same. But the main thing is, guys, the square root or power of a half are the inverse of the power of 2. So they kill that power on 2 if that's what we want. But now the question kind of arises, well, what happens if we want to kill the base? If we want to keep the power but kill the base? This is where the logs come in. So here's the same statement, but now I just want to kill this bit. How do I kill the base? And how I do that, guys, is I use a log with the same base. So that's what's critical. So we're going to apply log to the base 10 to our 100, and that brings us back to 2. So this bit kills that bit there. They're inverse functions. So that's where logs live, guys, is they're the kind of, they're the inverse function of a power that will essentially drop the power down to the ground. It kills the base. So we'll take a look. They are intuitively, guys, they're not as easy to understand as powers, but once you figure them, they kind of become quite straightforward to deal with. So as I was saying, logs are the inverse of powers. They don't have the same intuitive simplicity. So this 10 to the power of 3 is easy to explain. 10 to the power of 3 is 1,000. And the 3 just tells us how many times 10 is multiplied by itself. So that's something you could kind of explain to most people and they'd understand it quite quickly. The equivalent statement in the language of logs. The log of 1,000 to the base 10 is 3. And it just doesn't have the same. If you were to try and explain that to somebody, it's very difficult unless they were mathematically based, unless they had a good background in maths. That statement is very difficult to explain. But it's critical to understand, guys, that both statements are the same. They're both saying the exact same thing. So it's like I said here, was in the language of English, my name is Dave. This is like saying it in a different language, je m'appelle Dave. But there's no new information. The information is the exact same. It's just the language we're speaking has changed. So this is the language of powers. And this is the same statement in the language of logs. So it's just simply logs are often a different language. It's a very powerful mathematical language, as we'll see in the second lecture when we kind of delve into it a little bit more. But at the moment, we just want to get to grips with the nuts and bolts. So in this semester, guys, we're mainly going to be looking at log to the base 10. So as scientists, that's one of the main logs we would always deal with. If we were computer scientists, we would be dealing with log to the base 2 an awful lot because of the binary system. Log to the base 10, guys, is usually just called log. So if you see the word log on its own, it automatically means it's to the base 10. There's no other interpretation. Log on its own is log to the base 10 because it's the most commonly used log out there. Also, guys, as scientists, we will use this one, log to the base e. Now, we'll only introduce e in this lecture. Next semester, we'll start dealing with e an awful lot more, the exponential function. But we don't have calculators at the moment, so at the moment, we're just going to introduce it. So this is called the natural log. And from the French, it's the logarithmique naturel. That's where the letters ln come from. It's actually, so it's not in, guys, it's ln. So that's just a quick introduction. We will be using this a bit. We won't use this so much. We won't use this semester barely, but next semester we're going to be using this quite a lot. So main lesson from this, when you see log on its own, that means log to the base 10. So now we'll just take a look at a little bit of the maths of it. This, guys, is the essence of this lecture. This is really what I want you to kind of focus most on. Here's a statement written in the language of powers, and here's the same statement written in the language of logs. And often in school, you were told just to jiggle around the letters until things are right. That's not the right way to approach logs at all. So we'll take a look. So here I have a power statement. 3 to the power of 4 is 81. 3 by 3 by 3 by 3 is 81. We want to write an equivalent statement in logs. So this is how it works, guys. We have 3 to the power of 4 is 81. So what I actually want to do is kill this power statement. And how I do that, guys, is by removing its base. So in order to remove the base, what I do is I get the log of both sides. But because the base of my power is 3, I get the log of the base 3 of both sides. So this is what happens. I just simply write log to the base 3 on both sides. Now everything else stays the same. Now on the left-hand side, these cancel each other out because they're inverse functions. It's like saying the square root of x squared. The squared and the square root will cancel each other out because they're inverse functions. They kill each other off. in the exact same way this happens with logs. And the reason why it happened was because we chose a log with the same base. So now on the left, guys, we've got rid of the base, so the power has nothing holding it up anymore, so it just drops down. And then we get this statement here. And this, guys, now is the log statement. Now, usually to be polite, we write our log on the left. But both these statements are the same. I've just rearranged them. So now, guys, I've written, this is my power statement. And this is the exact same statement in the language of logs. So that's all we're doing at the moment, is just converting from power statements into log statements. We look at another one. Here we have 10 to the power of 6 is 1,000,000. And I want to convert this into a log statement, so I want to get rid of that base. So to get rid of the base, I need to use a log with the same base. So the base is the crucial bit. And now we apply this to both sides. Log to the base 10, log to the base 10. Everything else stays in. So it's critical to understand, guys, we're just doing the same thing to both sides. And now, as before, guys, log to the base 10 by base 10 cancel each other out. They're inverse functions. My 6 drops down. The power drops down. And now we have this statement here. So the log of 1,000,000 to base 10 is equal to 6. So power statement and the equivalent log statement. And again, guys, it's going to just take a little bit of settling to get used to the concept. There's more examples on the videos in Moodle as well, if you want to kind of explore things a bit further. Now, here's a weird statement, but it doesn't matter, guys. Don't be put off. It's nothing new. This is actually a power statement again, because we have a power. It doesn't matter that it's on the right. That's completely irrelevant. But now, so here's our expression, our power statement. Now, you guys haven't really met E yet, but it doesn't matter. We just know that's the base. So in order to remove that base, we use a log with the same base. So we're going to get log to the base E of both sides. Right in what was originally there. And now, guys, on the right is where the cancellation happens. We have log to the base E and E as a base. They'll cancel each other out. Our 2 drops down. And now we have our equivalent log statement. It's very important, guys, when you're writing these, the base sits down as a subscript. So do not write log E, that, so that is completely incorrect. So make sure, guys, you always use a subscript to describe your base when you're using logs. So we'll just take a look now. So now, guys, I want you guys to have a wee go at these. And if you need a bit more practice, guys, just watch the video on Moodle and you'll see more examples being worked out there. So don't forget to pause the video and then give each of these a go. So, like I said, and this is really, guys, the essence of this lecture. This is really all I'm asking you to do, to go from the language of powers into the language of logs. And then, as we'll see in the next few slides, go in the reverse direction. And that's the main essence of this lecture, the main learning outcomes. So I'll let you guys have a go at them. So on Moodle, you'll need to be able to write in your answer with the editor. Like I said, make sure you use a subscript when you're writing in your values. I'll push on now, guys, and I'm just going to go back the other way. Go from starting with a log statement. How do we get back to a power expression? So there's our power expression. I don't really like these, but I just put them up just because that's how it's usually introduced in the leave insert. But I prefer to understand what's going on. I prefer you guys to understand what's going on as well. So now we're working back the way, guys. Here we have a log statement, and we want to write it as a power. So let's start off with just write what we have. Log to the base 8 of 64 is 2. Now I want to kill this log. Now this might look a little bit weird, but bear with me. So I want to kill the log, guys. What will kill log to the base 8 is if I raise both sides as a power on 8. So this is going to just look a little bit odd for a moment. So both sides become a power on 8. And now we have this scenario. The reason why I made 8 my base, guys, was because 8 was the base of the log we want to kill. So now, again, using inverse functions, guys, if I have, say, the square root of x to be squared, so it doesn't matter the order in which inverse operators are applied, as long as they're directly beside each other, they cancel each other out. So now, that's what happens here. I have 8 as a base, and then log with the same base. They simply cancel each other out. That 8 goes as well, by the way. So the 64 just drops down. And now we have a power statement, which I think you'll feel feels a lot more familiar. So it's very important, guys, to understand that the same statement has been made. It's just the language has changed. So you would never, well, yeah, and as far as we're concerned, guys, you wouldn't have logs and powers appearing on the same line. It's either logs or it's powers. We do have these temporary steps, but they're just to allow us solve things out. So you're either talking logs or you're talking powers. You cannot talk both. Same as with normal linguistic languages. You either speak French or you speak English. You try not to do both. Look at another example. Log to the base 10 of 10,000 is 4. So I want to kill log to the base 10. How I'll do that, guys, my base is 10, so I raise both sides on a base of 10. So we get 10 on the left, 10 on the right. Log to the base 10. Once you get used to these, guys, you don't need to write this intermediate step, but I'm just showing you what's happening. These kill each other off. My 10,000 drops down. And now I just write my power on the left to be polite. That's my equivalent power statement. So essentially, guys, if you want to kill a log, you use a power with the same base. If you want to kill a power, you use a log with the same base. That's the key. We look at another one. Again, it looks really weird. Most of you won't have encountered this statement, but you just say, well, here's my log. That's what I want to get rid of. Its base is e. Log e of 20.09. So this is what I want to kill, log to the base e. So I'm going to raise both sides as a power on e. So the left becomes e to the power of 3, e to the power of log e 20.09. These kill each other off. My 20.909 drops down. And that's my power statement. And once you get quite adept at these guys, it's perfectly fine to go from one to the other. But so, sorry guys, actually that just looks, I'm just going to change the right on this just to make sure. So it's 20.09, just, it looked a little bit raised up there. So now I hope that makes sense a little bit, guys. Like I said, just watch the videos if you need to kind of get a bit more detail. Here's the old essential. And now we'll move on again. So again, pause the video and try and convert the following log expressions into power expressions. So just a quick history now, just to kind of put a bit of context on it all. Two guys were credited. Napier gets the most credit. He was quite an unusual man. Napier used to travel around with, he was a strong believer in the occult and black magic, and he used to travel around with a spider in a box, and quite an unusual character. And then Just Bergy was a Swiss clockmaker. So they were both working independently. They both came up with very similar versions of log. So they've both kind of credited with it. Napier tends to get more credit in Ireland and England because he was a Scottish Scot, whereas Bergy gets more credit on mainland Europe because he was Swiss. So but they're both credited with these kind of mathematical accreditation things are very common. Like calculus is another one. There's famous battles between highly intelligent people as to who invented something first. But both of these guys are credited with developing logs. Now, so as we were kind of seeing, guys, basically what happens is any number can be written as a power, and thus it can be written as a log. So I'll show you what I mean. So if we have 100 could be written as 10 to the power of 2. The log to the base 10 of 10 to the power of 2 is 2. Similarly, 100,000 is 10 to the power of 5. The log of 10 to the power of 5 is just 5. So this number here, now this log represents that number. This log here represents that number. I hope you'll agree. 0.001 is 10 to the minus 3, so the log of that is minus 3. And any number, guys, can be written as a power on 10. And once we know the power on 10, then we know its log. There's another one there. Now note, guys, this 7 is actually, because it's 4.76300. If we go to scientific notation first, it's by 10 to the power of 7. That's what that 7 actually represents. Same as this 5 here. It's the order of magnitude of the number. But we're not going to get too caught up in all of that. But essentially, guys, any normal number can be written as a log. And this made difficult maths much easier, as we'll see mainly in the next lecture, but briefly here. So log tables were used. So somebody, his name was Briggs, very shortly after Napier published his invention, this guy Briggs produced what were called log tables. And this is what log tables looked like. So this table, guys, the log tables were used to convert numbers directly into logs. And then once you'd done your maths and you got your answer was now in this language of logs. So we would go to anti-logs, and anti-logs would convert our log answer back into a whole number, but they were just inverse of each other. Each table was simply an inverse of each other, but by using the tables you didn't have to do the intermediate calculations yourself. So for us in school, guys, like those tables were like you guys would reach your calculators. So any number can be written in scientific notation and then very quickly turned into its log form. And you don't even need, once you knew what you're doing, you didn't have to do the scientific notation step. You could move quite quickly into the log form. So the log tables and anti-logs were developed. And most school kids up to 20 years ago would use their logs instead of their calculators. So when I did my intercert, which was before the junior cert came along, we had to do most of our maths using log tables. There was no calculators. They barely existed and they weren't allowed anyway. So calculators, guys, really are only effectively 30, 40 years old tops, as in readily available to normal people. But maths has been around since basically humans started kind of counting mammoths and deciding how they were going to catch them. So logs were a very large part of most school kids' lives as they kind of progressed through maths in college. So just try and kind of imagine trying to compute a value like this without a calculator. It's extremely difficult, guys. Like, what you would have to do is simply guess a number, multiply it by itself 3 times and see how close you came to this. Then you would say, okay, my first number needs to be bigger. I'll make it a little bit bigger, multiply itself 3 times. It's an iterative process. It is valid, but it's hideous. I would imagine, guys, if I gave you a calculation like this, it would take most people kind of the guts of several hours to come up with any kind of an answer that was accurate within a couple of decimal places. With logs, guys, what you actually did was you use your log tables to turn that into a number. Now the number, because it's 3.38 by 10 to the power of 8, the log value, say, would be 83761, something like that. That would be the log equivalent of that. Because of the cube root, guys, remember cube root is to the power of a third. What a student would actually do is simply multiply this answer by a third. We'll see this in the next lecture. So all you would have to do, guys, is divide this log by 3. And then once you got your answer, you would go to your anti-logs and that would turn it back into the whole number. So instead of trying to do this horrible problem, guys, all you had to do was look up this value, the big number, divide it by 3 and look up the answer. So that's how logs made calculations very, very simple. Similarly here, imagine trying to do that value there. Again, take you ages to do it. Whereas with logs, it was essentially a very simple calculation. Well, not simple. We would turn this number into a log because it's 3.05 by 10 to the power of 5. The log version, guys, would be, say, 5 point something. 5.73. I'm just making this up. I have no idea. But now, guys, so we turn this number into a log. And then all you'd have to do is multiply it by 9.2. You'd get your answer, which is obviously going to be somewhere around 46 point something, 45. And then, guys, you go to your anti-logs and you get the answer. So instead of basically logs made hard maths much, much quicker. Instead of doing this thing, all we had to do was multiply a new number, the log, by 9.2, get our answer, and then switch back to the whole number value. Now, we won't be doing anything like this, guys. It's completely kind of irrelevant now with calculators and stuff, but it just shows you that kind of what were very, very difficult calculations, logs made much, much simpler. And as Pierre-Simon Laplace said, Laplace was one of the huge godfathers of maths. There's Laplace transforms. There's all the, like, Laplace is, engineers use a lot of Laplace work. He covered huge areas of maths. He'd be one of the big four figures of modern maths. So Simon Laplace called logs an admirable artifice, which by reducing to a few days the labour of many months, doubles the life of the astronomer, and spares him the errors and disgust inseparable from long calculations, which I think you guys know without, I'll emphasise that, the disgust inseparable from long calculations. I've been putting you guys through that, but I hope you'll appreciate it's for good reason. So guys, we'll finish up there. That's kind of logs, that's the introduction. The most important lesson of this lecture, guys, is that logs kill the base. And then if you need to kill a log, you raise both sides onto the same base. So if we need to kill 10 to the power of 3, we need to use log to the base 10 to do that. So just when the main thing, guys, is that the bases are the same, and then you can use them to kill each other off. In the next lecture, lecture 12, we'll start to take a look at some of the maths, but really as a way to develop the set of log rules. So there's a set of rules for dealing with logs, just like we saw there was a set of rules for dealing with powers. But I think that's enough for the moment, guys, so thanks for paying attention, and we'll chat to you in lecture 12.